So I'm going to tell you a little bit about work done with Lee Altenberg, who's here and going to talk after me, and with Lilach, who's here and already spoke, and also with Uri Lieberman and Mark Feldman. And it relates to my main interest, which is the evolution of the mechanisms that generate and transmit both phenotypic and genetic variation. And I'm trying to study this idea of both in terms of biological evolution or genetic evolution, as well as cultural evolution. So I'm going to start with Darwin. So Darwin said that some authors, this is a case where I guess he didn't want to commit to the saying, so he said that some authors, someone else, believe it to be the function of the reproductive system to produce individual differences as much as it is to make the child like its parents. Right? So this is essentially is talking about some balance that the reproductive system has to make between making the child like its parents, because if you're able to produce children, then they should be like you so that they will be able to produce children as well. And on the other side, to produce individual differences because circumstances change and there might be better competitors, different ecological situations, etc. And we can summarize this as a balance between fidelity in terms of transmission and generation of variation, a balance between fidelity and variation. And there are different examples for this. A lot of my work was on the evolution of mutation. So Sturtevant in 1937 talked about, on the one hand, he talked about a high frequency of new mutants that cause appreciable reduction in viability. So you don't want mutations because most of them will do bad things. This was from his insights from flies. And on the other hand, he talked about favorable mutations, which are the only raw material for evolution. Right? So this is a balance between the effects of deleterious mutations and the effects of beneficial mutations. And we can think about a similar balance for migration, where some individuals will prefer to do homing, stay where they are, and some will go for migrating to a different site. Learning, some individuals will imitate their parents, some individuals will innovate and use new behaviors or new technologies or new ideas. Or similarly for learning, something that's more been talked about in, I guess, machine learning is and the reinforcement learning, exploitation on the one hand, use the knowledge that you already have, and on the other hand, exploration, try new strategies. So now I'm going to show you a very general model that we developed for studying this balance, and three more specific models that relate to mutation, migration, and learning. And this is work published in TPB in 2018. So the general model, we assume that in the population we have several different types, and we mark them A1, A2, AN. And these can be different mutants, different sites, like locations, different behaviors. Each type has a frequency in the population, so F1, F2, etc. And each type has a fitness, W1, W2, etc. And the fitness is basically the relative reproductive success of each type. Right? So we have 4 types here just for representation. Of course, we can have more. Now, apart from that, we also have transitions between types. So in the individual that was born to be type 1 can transition to be A2. And these transitions happen with probability here. We call it CK. That's the probability to leave your type. So CK is the probability to leave type K. Where do you end up? Well, where do you end up? It depends on MJK. So if you leave type K, the probability to end up at type J is MJK. So the probability to transition from K to J is the probability to leave K and then end up at J. Okay, and once we set up this, we can write a matrix equation that describes the change in the frequency of the different types over consecutive generations. And this is the equations, and I don't want to bore you with the mathematical details, so I'll just glimpse over it. We have a population mean fitness here, the frequency of the different types in the next generation. I minus C, this is the probability of not transitioning, not changing. C is the probability of changing and then changing to what, right? M describes to what do you change. So to stay at a specific type, you either don't change or you are born to another type and you change to this new type. And D describes the effect of selection through fitness. So this is the equation that we use. And like I said, there are a lot of mathematical details, so I'm sort of skipping over it. So three more concrete models, because this is very, very high level. Three concrete models that we can describe here. The first is a mutation model where each type, A1, A2, AN, describes a different allele. So we're thinking about a single locus and the different alleles at this specific locus. And each allele has some fitness, right? Contributes to the fitness of the individual in some way. CK will then be a mutation rate of this allele. So we think about an allele that somehow may contribute to the mutation rate of the individual, or at least the locus. And then you can think about, well, what is the probability to mutate from one allele to the other, and set that in M. Another kind of mutation model, we can think about AK as an individual that has K deleterious mutations. So the population individuals accumulate deleterious mutations, and the deleterious mutations are then acted against by selection, so purged from the population by selection. So AK is an individual with K deleterious mutations, and WK then will be the fitness with those deleterious mutations. And CK will be the mutation rate of an individual that has K deleterious mutations, that accumulated enough mutation. And then mutations can be either deleterious or beneficial. Here beneficial will mean compensatory, somehow fix something that the deleterious mutation has broken. So this is another example. And a totally different example is a migration model. In this case, we're thinking about AK as individual in some dim or site K, so the population is spread around in different locations, and each location has individuals, and the location determines the individual fitness. And CK then will be the probability to leave your dim, to leave your site. And we can think about different migration schemes. So if we're looking at what M looks like, what is the probability to move from one location to another, we can think about different location schemes. For example, here, individuals can only move to the next site. So you can think about some ocean current, for example. There is a strong current, and you have to migrate with the current if you're migrating. Or another example is you can move to any adjacent location. So this is around a lake or around a mountain range or something like that. And if you're interested in this kind of migration schemes, Carlin had a very a big and nice paper full of these migration schemes and interesting results from those for those models. Lastly, a learning model. In this case, we think that AK is some phenotype or behavior K, where K is an integer. For example, the number of hours to invest in foraging, or the number of hours to prepare for a talk. WK is the fitness of the phenotype that forages for K hours. And CK is an exploration rate of phenotype K. That means what is the probability that instead of using the phenotype that you got from your parent, you're going to try a different phenotype. You're going to try a different behavior. In this case, CK will be exploration, and 1 minus CK will be exploitation. And then M will be the exploration breadth, right? If you're exploring what are you likely to explore. So these are sort of 4 more concrete models. They are still very high level and theoretical, but a bit more concrete than the general model. Right, so I showed you a general model, and then a single locus model, and a multi-locus model for mutation, a migration model, a learning model, and really we think that there are more models and more things that can be modeled through this general model. Obviously not everything, but we think it may apply to more scenarios. So some results from our general model. So the first thing that we're looking for is for an equilibrium. We're looking for some special f. F here, I remind you, is the frequency of the different types. Right? It's a frequency vector for the different types. We're looking for some special f that won't change over time, an equilibrium of the system. And from some nice mathematical properties that we have for the different parameters of the model C, M, and D, we can find through the Perron-Frobenius theory, we can find that actually there is some equilibrium. So there is a F star, some frequency vector that is stable, and W hat star, that's the mean fitness of the population, that will be stable. And in mathematical terms, the mean fitness here will be an eigenvalue of this matrix, and F star will be the eigenvector of this matrix. So this relates sort of the evolutionary model to the Perron-Frobenius theorem. So the first result that we find here, we called it the modified mean fitness principle. And this is the basic result, that if you have an individual AK with fitness WK that is below the mean fitness of the population, then increasing transition out of this type will increase the population mean fitness. Right? So if below average individuals increase their transition rate, that will increase the population mean fitness. In mathematical terms, what we see, our result is that the sign of the difference between the mean fitness and the fitness of the individual equals the sign of this derivative. So if this is positive, meaning that the fitness of the individual is lower than the mean fitness, then this is positive. So increasing transition out of the type will increase the population mean fitness. Okay, so below average, it's beneficial for the population if below average individuals increase their transition rate, if they stop being their type and try something else, if they mutate, if they migrate, if they explore. Right? But this is a population level advantage. And as Lilach mentioned today, there is a contrast many times between what the population wants, the population level advantage, and what the individual wants. Well, I'm saying wants in a quotation, right? The individual level. So, and the result that I just mentioned, we already saw a glimpse of it in a previous paper where we found that increasing the mutation rate of below average individuals will increase the population mean fitness. So this is a basic result, part of what's called stress-induced mutation, that suggests that even in a constant environment, it's best if below average individuals increase their mutation rates. So this is the modified mean fitness principle in action on stress-induced mutation. So if I'm now, I showed you a result for the population level. So what happens at the individual level and at the sort of the gene level? So to talk about the individual level, I want to mention another concept in evolutionary biology, Fisher's reproductive value. So this is, of course, Fisher, R.A. Fisher. He would do very nice today with the hipster culture, as you see. And Fisher's reproductive value is the relative contribution to the long-term population. So an individual's long-term contribution to the population is called his reproductive value. Whereas fitness is the Fisher, at least in Fisher's eyes, fitness is the contribution to the next generation. So a corollary of the result that I showed you about the modified mean fitness principle is the reproductive value principle. This says that if the fraction of long-term population descending from type K increases from transitioning, then increasing the transition from AK will increase the mean fitness. So basically now we say, before we said, well, if you are below average, you should transition, that's good for the population. Here we say that if it's good for you to transition, if by transitioning you'll contribute more to the future population, then that's also good for the population. That will increase the mean fitness. Right? So this now connects between the advantage at the individual level and the advantage at the population level. So we have those two levels, but of course, evolution in many cases occurs through the gene level and not through individual or population level. So it's good for the individual, it's good for the population, but will it actually evolve? So in the next step, we also looked at evolutionary genetic stability, which is a method to assess what happens at the gene level. So what we imagine is a modifier locus, so a specific gene, or a gene complex maybe, that controls CK. It controls the transitions. It controls the mutation rate, or the migration rate, or the exploration rate. It modifies these rates. And we start with a population where everybody has, in this modifier locus, everybody has allele little b, with rates C1 to Cn. And we ask what happens if we introduce a new allele to this locus, an invader allele that has different rates, C'1, C2, C'2, etc. What happens? Will this big B allele be able to invade a population and increase in frequency? And we're looking for some little b that cannot be invaded. That will be called evolutionary stable. Right? And now I'm actually thinking about what happens to the modifier locus. I'm thinking at the gene level. So we have to take our previous model and add a new equation where f is the frequency vector for the resident allele, and g is the frequency vector for the, sorry, it says here resident twice. That's a bad copy pasting. G is the frequency for the invader allele, big B. And what we now, before I show you the result for this, I want to mention here the reduction principle, because this kind of analysis has been done before by Lee and Uri Lieberman and Mark Feldman, but for a specific case in which transition the transition rate doesn't depend on the type. So the rate of transitioning is the same for all types. You can't choose that only below average individuals transition with high probability and the rest stay the same. You have to have everybody use a uniform transition rate. If that's the case, then according to the reduction principle, an invader allele big B can invade the population only if it decreases the transition rate. So a mutator allele can fix in the population only if it reduces the mutation rate. A migration modifier can invade the population only if it reduces the migration rate. Okay, but of course in our case C is not constant and uniform, but it can depend on the type. So the result that we find here, which we call evolution of increased genetic variation, is that big B can invade the population if it increases transitions specifically from types that are below average. Right? So if individuals with below average fitness, right, their fitness is below the mean fitness, so the right-hand side will be positive, that means that if we increase their transition rate, lambda will increase, where here lambda is the eigenvalue of the Jacobian of the system, which is a way that we can say if big B is successful in invading the population. So if the allele B increases the transition out of the below average fitness, it will be able to invade the population. So this closes the 3 levels. Here we also find a gene level advantage to increasing transition out of below average individuals. So to summarize this, we find that increased transition from below average individuals increases the population mean fitness. It's expected to evolve both because of a individual level advantage and a gene level advantage or a modifier stability. And something that we have to mention here is that we assume that big M is irreducible. What does that mean? Because that's an important assumption here. Big M said, what is the probability to move from one type to another? For big M to be irreducible, that means that I can move from any type, I can transition from any type to any other type in a finite number of steps. Okay? That means that, and that's an assumption of the model. So everything I said builds upon the idea that if I'm below average, I should transition because this assumption is true, that means that in a finite number of transitions, I will have a descendant that will be above average. So the whole thing depends on sort of mobility, right? If we're talking about mutation, then it's genetic mobility. If we're talking about migration, then it's ecological mobility. And I can imagine, but I haven't done any proper analysis of this, that this can work for social mobility as well, right? So if there's no way to go to a better type, then there's no reason to try and leave your type. So some outlook on additional work that we plan to do regarding this is to look more at cultural transmission, learning and other forms of cultural transmission in which cultural traits like technology, language, behavior, norms, beliefs, are transmitted between individuals, and in this case, many times culture is not vertically transmitted from parent to offspring, but rather horizontally transmitted between peers and obliquely transmitted between generations. Another type of transmission that we have already have a preliminary result about is frequency-dependent transmission. That's the case in which the probability for me to leave my type depends on the frequencies of all types. For example, you might think that if I'm part of a rare type, right? If I'm part of the minority, then I'm less likely to leave my type, right? Because maybe my parents are more strict with me remaining the same as they are. Whereas if I'm part of the majority, then I'm more likely to, go and explore new behaviors because I'm part of the majority. I feel very protected and safe. Another route to continue this work is to analyze models for combination and sex, continuing on Lilach's abandoned sheep principle, and the mathematical analysis is, I guess, much more complex in that sense, but it might also lead to interesting results. And another direction is, like I said, transmission of social traits like social rank and social status and similar things. So with that, I conclude, and if you have any questions, I'll be happy to